All right, so before we get any further, if you're still in pain from histogram, don't worry, it gets worse. So part two of histogram we'll be talking about today. It's called Huffman Coding, and it will be using the results of your histogram part one in part two, which is called Huffman Coding, which is traditionally given as a junior level data structures assignment. So if it is too hard for you, Min Curley proposed a alternative assignment, which involves bit fields and inheritance. So what you're going to see on Canvas is a assignment called Double Trouble or something like that. And basically you will have the option of doing one of the two assignments or both for extra credit. One would be doing the bit field assignment, which involves bitwise and or not, that kind of stuff, with a little bit of inheritance, a little bit of teaching about different ways of doing consts in C++. We'll talk about it probably towards the end of the class. And the other option is a partnered assignment. So Bitfield is individual and Huffman Coding is partnered, and you can do one or both or neither, I guess, if you've got a high enough grade to be happy. So we'll start off today by talking about Huffman Coding, and then towards the end of the class I'll kind of go over the inventory assignment and things like that. So just be aware that Huffman Coding is considered a fairly advanced topic. I've given you a bunch of starter code and things like that to take away some of the parts that aren't really important to get across. What is important to get across is that you're going to be using a priority queue and a trie and probably a vector together, moving things around between them to solve a very interesting problem, and that interesting problem is text compression. So Huffman Coding is a provably optimal, given certain constraints like one character at a time, text files. It is provably optimal text compression. So you have Hamlet, and you can compress it down at like a 1.3 to 1 ratio or something like that. We don't care as much about hard drive space these days as we used to, but whenever you're sending bits across the network, networks are never as fast as we want them to be, and so it's still fairly common to do various compression schemes, Huffman Coding being one of them. There's better encoding schemes if you start looking at words rather than just raw letters, and as far as like images and movies go, there's different encoding schemes that are tuned towards images and movies and things like that. But as far as like a single character at a time processing and compressing them, Huffman Coding is provably optimal. So we're going to get into that in just a second. So there's also going to be a end of the year party, and the end of the year party will be on May 20th. And the party will involve playing Smash Brothers and Age of Empires 2, which just came out with a DLC for various Indian nations. I guess AoE 2 used to have a nation just called the Indians, as if, you know, all the different cultures of India are the same, you know, as if the Mughals were the same as the Vijayanagar, or however you pronounce it. And so they've had a DLC that just has different civilizations of India. It's kind of interesting. I'll probably have to brush up on my AoE 2. I haven't played it in a while. Anyway, that'll be on May 20th in person at noon in AC 1114, which is the computer lab for those of you that are online. I've never been there. All right, so LAN party at school. It'll be like noon till late. Maybe I might even start earlier, because we usually have such a good time. We typically go over our time limits. So, right, you're taking the day off. Excellent. So come up, potluck some food. You know, bring some food in. It's usually a good time. It'll be nice to meet some of you that I've never seen online. All right. So I want for now everyone to grab this file. Right now, it is the trie that we were working on in the last class. And you can see here that we've got a trie, and the trie represents the entire tree. Each individual node of the trie is represented by this node class. It's in the private section of the trie class, so main can't know anything about the nodes, or main can't know anything about root, things like that. Standard separation of concerns. Main has absolutely no reason to know about it, so it doesn't. some students were asking why I am using shared pointer after last time I went on a bit of a spiel about why unique pointer is the correct pointer to use. And the reason for that is because there's a hole in the C++ standard. Smart pointers are used to represent ownership, like who owns the memory. And what it means to own memory means it's your responsibility for freeing it, right? Anybody can get pointers to that memory and look at it and maybe even change the values there, but they can't delete it. Only the owner of that memory can delete it. And shared pointer means there's shared ownership. In other words, that two different people own the same block of memory. Like let's say you have a tree, a binary tree, and then you've got a vector, and some of the elements of the vector point to parts of that tree. If you were to delete that node out of the tree, then all of those pointers to it from the vector would be invalidated. And that's bad. Now you have pointers, dangling pointers that are pointing at nowhere. Whereas if you use a shared pointer, if you remove the reference to it from the tree, it doesn't free that memory because it's a shared pointer. Shared pointers keep a track inside of their heart of hearts how many pointers there are to that spot in memory, and every time you copy it, it increments the counter by 1. Every time one of them goes out of scope, it decrements it by 1, and only after the counter hits 0, meaning there are no pointers to this anywhere in the world, does it free the memory. That can cause problems if you have like a circular linked list and you have pointers pointing both directions. You can't really ever delete anything. Even if you delete the list, there's still pointers to people, and so it won't get freed. And so there's something called a weak pointer that is a shared pointer but doesn't give you a +1 to your reference count. None of that, though, really helps with our problem here, which is that we have a tree and we want to iterate down it. And so what we had before was a unique pointer, which is the proper way of representing the ownership, because each node is owned by one person, its parent. There's one parent for every child, and that parent owns it. When the parent goes away, the child goes away. However, there's a hole in the standard, and the hole in the standard is there is no smart pointer used for just iterating down a tree of unique pointers. You can't copy a unique pointer. So if you wanted to do something like this, if here, like you have a pointer called temp, and you want to duplicate it so you can run down the tree, there is no smart pointer in the standard for that. There's something in the experimental standard which probably won't make it in because Bjarne has said he doesn't like it. There's something called an observer pointer that is done for exactly that purpose. You have a tree of weak pointers, and the observer pointer can start at the root, copying it, but not copying it. It doesn't take ownership. It's just a pointer. And then it can run down the tree and actually read and write values and things like that. Observer pointer is kind of a dumb name because it doesn't just observe. It can actually change the values on the way down and stuff like that. But the point is that it doesn't change ownership. And so the official response to this is use a raw pointer, right? So if you had a unique pointer, unique pointer to a node, root or something like this. Call it root 2 so I don't get a conflict. If you want to make a pointer to it and iterate down the tree, you would do something like this. You'd make a node pointer, just a raw node pointer called temp, and call root2.get, like that. And so that returns the internal pointer to it. I don't like that solution because I don't like raw pointers. And there's nothing, people will say there's nothing wrong with a raw pointer, right? It just points at an address of memory. And they're right. Like you still need to know raw pointers. It's not like you're going to get rid of them or anything like that out of the standard. Like it's not going anywhere. But they're also wrong because a raw pointer, to me, the more that I've kind of gotten like into the philosophy of things, I don't like them because they're not a complete type. I've become kind of more of a strict type person, kind of moving away from the Python into like I want more strict types. And a raw pointer doesn't tell you how many elements it's pointing at. A smart pointer does. A smart pointer, a shared pointer to node tells you you're pointing at exactly one node. No more, no less, one, right? A raw pointer could be pointing at one element or it could be pointing at 5 elements. And so you have to pass the raw pointer a size with it. And so the very obvious point is the type of a raw pointer by itself is incomplete. It doesn't have enough information for you to be certain that you're using it properly. And so if you were to pass a raw pointer, like here, I have this recursive print function that we're going to write in our lab time today. So you're going to pass a pointer to root down here, in the public section, we have a method called print Trie. So we call print Trie, and it's going to print all the strings within our trie. Okay. And now main doesn't know anything about root. It shouldn't. It doesn't know any of the implementation details, which is good. And so we have in the private section this function called recursive print root. And I'll explain what this is in a little bit. If we passed a raw pointer as root, which you would have to do if you're using unique pointers. A unique pointer can't be copied, right? You would call .get, get the raw pointer out, pass it to the function, and that thing would run through the thing. And it's kind of up to you to make sure that you don't delete something accidentally, right? Because if you have a raw pointer, a lot of times you don't know, am I the owner, am I not the owner? Idiomatically, if you're using smart pointers, using a raw pointer means you don't own it. But that doesn't stop you from screwing up. And over the years, a lot of people have screwed this up. And when they finish with a pointer, they'll call delete on it. Like, I don't know if I need this anymore. So they delete it, right? And there's nothing in a raw pointer that stops you from deleting it. And that breaks everything, right? And so it doesn't convey ownership information, and it doesn't convey the size. And so I sort of philosophically don't like using raw pointers. And so I did something bad, actually, here. This is not actually good coding. But I did this because I sort of am philosophically opposed to raw pointers, and there's nothing in the standard that kind of meets this specific need. There is something in experimental, and it's probably not going to make it into the standard, so I'm not going to even bother teaching it to you. So I'm just using a shared pointer instead, and this is bad. So don't quote this as being like philosophically good C++, because what I'm saying here is that multiple people own the memory in a tree, and that's not true. The only person who owns, remember, own means I'm responsible for deleting it. There's only one person who's responsible for deleting a node, and that's its node's parent, right? So what I'm doing here is bad, but at the same time, it avoids the pitfalls of using a raw pointer, which is, to me, just a bad type. I don't like raw pointers as a type. Like, philosophically, I don't like them. So, taking the day off to go. Cool. All right, so yeah, that's why if you saw the last video, I switched from unique pointer to shared pointer, because it would have pushed me into using a raw pointer, and yeah, so I probably should have. That's the correct answer, is to use a raw pointer. I don't like them. So this is also less efficient. Every time you copy a shared pointer, it increments a reference count. Every time one goes away, it decrements a reference count. There's a bit of an overhead, not a lot, a little bit of an overhead in it as well. Okay. So what we want to do is we are given a trie. You are going to write this function in lab time right now. Okay. It's about 4 lines of code, just so you know. But I'll give you time to write it, because recursive things kind of take your brain and sort of go, in different ways. So let me just draw out let me draw out a trie for you, and then you can write this function. Okay. So let's pull up OneNote here. Okay. This is 41. Try it. All right. So the root of a trie doesn't represent anything. It's just the root. Here's root. Root's pointing at here. And then each node has 26 kids, right? One corresponding for the letter A, one corresponding for the letter B, so on and so forth. So let's say the fourth one, index 3, which is the letter D. This is the letter D. There's a node for that. All the other ones are null. And then we've got one in the O direction, and that is a leaf. Let's say it's not a leaf in the sense of like it's the end of the tree, but like it's a word. Do is a word. And then we've got one in the O direction from there, and one in the direction from there in the R direction. So door, D-O, R, K. Dork is a word, door is a word, do is a word. In the L direction, and in the L direction. The direction isn't like, whatever. It's 26 pointers. I'm not going to be able to lay them out precisely. So you can see here we got do, doll, door, dork. I don't know. Dolt. Dolt is a word. Okay. All right. And how do you copy the file to your terminal? Copy. Yeah, CP. Copy / public / trie.cc space dot. Dot represents your current directory. And then you can do the lab time. Okay. So what you want to do is write a function that will print all of the words, not the whole tree, just the words. Okay? So it's going to print do, doll, dolt, door, and dork in that order, in alphabetical order. All right? And remember, each individual node here, if you zoom in on one of these nodes, it just is, there's kind of nothing there. It's just a bunch of pointers, right? I think we got a count also. We have a count, we have true or false if we're actually a word, and then just 26 pointers to kids that are by default null. And so how do you get what words you are out of it, right? They don't have a string as part of their structure. So what's really interesting about tries, and this is kind of where we stopped last time, is that when you traverse a trie, which is a tree, you build up a string corresponding to the thing. So when you call recursive print, it starts off at root with empty string. And then when you go in the D direction, what you do is you take the string, which is empty string, and you say the string is equal to the string plus the letter D. And now the string is here as D. And then when you pass it in the O direction, you append O to D, and so you know that this spot here is do. And since that spot is a leaf, you're going to see out do to the screen, do the do. And then you go in the L direction, that spot's not a leaf, but you append the letter L to do, and you get D-O-L. And then you go in the L direction again, and you append an L to it. And so what you're going to do is, and that's a leaf, so you print doll to the screen. So what you do is recursive print starts off at root and empty string. And then every time you've got a kid that's not null, you recursively call in that direction, appending the letter corresponding to their place in the array, right? So if they're an array, if they're child 0, they're the letter A. If they're child 1, they're letter B. And if you char C is equal to A plus I, something like that. So you're going to iterate from I equals 1 to I is less than 26. And you just basically, that's how you make a letter, right? And you append that to the string, and then you recursively call down that way. And then if the pointer you're at right now is a leaf, you print out string. And that's it. It should be about 4 lines of code. Check for null pointers, make sure you don't recurse infinitely. But basically just have a for loop that says for each of my children, recursively call down into it, and you are going to append, S is equal to S plus C, right? Something like that. So you're going to have a for loop and something like that inside of the for loop. And that will build the string as it goes down. And then, if temp is a leaf, you print the string. So I'm going to give you guys 20 minutes to write 4 lines of code. All right? Portnoff, what does the monkey on a ventilator mean? Is this too painful? What is the, is this too hard? It's 4 lines of code, man. Your head hurts? Yeah. It's recursion. It's supposed to hurt. It's good. It means it's working. So again, every time you recurse down, you're going to append the letter corresponding to which child that is. So if it's child 3, it's going to be S is equal to S plus the letter A plus 3, right? ASCII codes, right? This is going to be inside of a for loop because you got 26 kids, right? A plus 0 is A. A plus 1 is B. A plus 2 is C. A plus 3 is D. So the third time through, is my third kid real? Is it not null? Yeah? Okay. Then let's make a character, append that to the string. You do that in 1 line if you wanted to not make this variable. Doesn't matter. And then you just append, and then you recursively call down. Recursive print my D child, right? That's it. Okay. Are you using the other member functions? I mean, I added in spell checking, didn't I? Yeah, I did that in the previous class. You don't need to worry about this. Aaron was like, could you just make it so you can only add actual English words to it? And I was like, sure. And so in just like, kind of like 3 lines of code, I've added spell checking, right? So this opens the dictionary file on disk. In Unix systems, that's where the dictionary is. If I couldn't find it, it kills the program. I then make an unordered set. I make a hash table of words. And so every word possible, every combination of characters, every string possible is either a word in the English language or not. And by default, none of them are in there. And then I do a 1-line parse the dictionary and put it into the data set. And so it says, while the file still has stuff in it, add to the English language, insert into the English language, the uppercase version of read a string from the file. And so it's going to read a string from the file, uppercaseify it, insert it into the hash table, and it will do that until until you're done. And so in 1 line, it loads the entire dictionary into a hash table. And then if you want to see if a word, every time the user types in something, if that word is in the English language, we add it to the trie. If not, we get a America error, freedom not found. So, yeah, so this code is calling insert. It is calling the other stuff. But basically all you have to write is this function here, the print. And it's going to print all of the words that have been added to the trie. Okay? So main calls this function here. This function calls the recursive version up in private up here, and you're going to recurse down through the tree, building the string as you go along, and every time you hit a leaf, you print the string. And if you do it right, it'll come out alphabetical, even. Okay. Good luck. Have fun. 20 minutes begins now. Pause in the stream. All right, and we are back. So, first thing to start with, you can always check for null, right? What if you get a null pointer passed in? It's always a safety issue right there. Okay, so if we're a leaf, so if you print, a node in your leaf, you print yourself. So if temp points to leaf, then we are going to see out the string. And we can, let's print out the count too. So we'll get how many times the word hello has appeared as well as hello. It'll say hello, 5, or whatever. And then we just need to recurse down into each of our children. So parent I equals 0, I is less than size, I plus plus. Temp points to children, square bracket I is going to be the child, the ith child. Okay. And so we're going to recursively call, so we're going to do a recursive print, passing in the first child, second child, third, as we go through the for loop. And then here's the key thing here. We're going to add to the string the letter of that kid. So if we're going to the kid that corresponds to A, we're going to glue A onto the end of the string. If we're going to the kid that corresponds to Z, we're going to glue a Z onto the end of the string. So I'm going to do this with char. Letter A plus I. Just like that. Okay. So 0 plus capital A is capital A. Remember, single quote is an ASCII. Like, there's no actual letters here, believe it or not. Capital A is 65, right? So 65 plus 0 is 65. So the first kid is going to get the letter A glued on to whatever string we have. So if we're in the middle of the string somewhere and we got hello, and we have an A child, it would be hello A. Okay? We're doing all caps, we're not worrying about uppercase, lowercase stuff. And yeah, I think that's it. Let's try that out. See how that works. Anyone want to take a bet? Is this going to work? Segfault? What do you guys think? What do you think? Segfault? Yes or no? Place your bets now. You'll always believe. Thank you. Yeah, last time. That was an interesting bug last time, actually. All right, run it. Hello, 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 hello. Goodbye, world. Rolled. Oh, no. Not an English word. See that? Works. The spell checking works. Hello, 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 goodbye, hello, world. Hi, ha, 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 ha. Ho, ho, ho. Santa Claus was here. Okay. String to search for Santa. In the dictionary, Santa's not in the dictionary. Cool. Didn't break anything there. And then here we have the tree. You can see it's all alphabetized. And we have Claus, goodbye, ha 6 times, hello 4 times, ho 3 times. There it is. Easy as that. So, all right. So that is, I don't know what was it, 6? I don't know. Okay, so more oh ye of little faith, thinking that I was going to segfault. Holman, no confidence in your professor, huh? No confidence. 4 lines of code. Look at that. And we're iterating through a trie. And as you go down, you just append to you just have a pointer and you have a string that goes with the pointer. And the pointer is going to go like that. And as the pointer moves in the A direction, the string gets an A. It moves in the D direction, it gets a D. You know, and so as these things go down, and then when you pop off the stack, the string rewinds as well, because this is actually a string by value, not a string by reference. We're actually going to make a ton of strings, and this is not super optimal. But if you passed it by reference, then the parent string would change as well, and everything would break. So, yeah. So yeah, it's just easy to code. 4 lines of code. There you go. Quite complex behavior, and it generates strings for each of the children. Any questions? Yeah, that makes me feel a little like all those extra copies, you know, we're making, but it works. Thank you, Holman. Bowing SpongeBob. Yeah, thank you. Yeah. So, yep. The predictive text thing. I don't know where we're at with that kind of thing over here. Predict. We'd probably need to redo that so it's the same thing, right? So it would have a string, and we can actually print the string of the biggest child and things like that. You probably, in fact, use the recursive search. Print. I don't know. You can probably adapt this code to make a better predictor. Right now, the predictor is, I don't know. You don't understand that. Okay. So what is single quote a single quote? That is a number. That is an integer. C++ doesn't have a very clear delineation between letters and numbers, to its detriment. And the reason for that is backwards compatibility with C. Right? A character holding like like an actual character of English, like the letter C or the letter A or whatever, could have been its own type, right? It could have been its own type, and that probably would have made a lot of sense. But it's actually an integer. And it's really annoying because sometimes you just want to have an 8-bit integer. Like if you just want to have like, here, let me just show you something. Like what if you're just going to have numbers that range from like 0 to 255, right? You know, you could have an unsigned integer 8, you know, T named Bob, and Bob's value is 10. And we can have an unsigned int 8 P named Sydney, and Sydney's equal to 55, and we see out, you know, Bob plus Sydney equals Bob plus Sydney. Anyone want to take any guesses on Discord what this is going to print to the screen? You just got a standard 8-bit integer. This is an integer. It says so right here. It's an unsigned 8-bit integer. Possible values range from 0 to 255. You know, maybe we do it this way because we just don't need any more bits, right? We want to be efficient and you just want to print the values and stuff. No idea? This is a trick. You're right. You're damn right it's a trick. I'm just trying to print numbers. I'm trying to print 10 plus 55 is 65. And I got, what? Huh? I didn't get the letter A. You thought it was going to be the letter A. I didn't get the letter A. But I certainly did not get 10 plus 55. So what the hell is going on here? Well, what is 10? 10 is new line. Okay. So it printed a new line there. Look. That's a new line being printed out. And 55, oops, 55 is the number 7. So instead of printing out 55, it printed out 7. And instead of printing out 65, wait, it did print out 65. What's going on there? Well, what if we made this a uint8t? Like that. Now we get the letter A. How are these not numbers? Exactly my point. So, Murica error. Yeah, fair enough. Okay, freedom not found. Better dead than red. Yeah. So this is a yeah, it's an annoyance. It's because there's not, even though it's an unsigned 8-bit integer, C++ treats it as a character, and so it will print the ASCII code very helpfully for you. Instead of getting the number 55, you get the number 7. You're just like, I just want an 8-bit number. I don't want you to be turning everything into ASCII for me. What the hell, you know? And it's just super, like, aggravating. If you actually want to see the numbers, you know, make it an integer or whatever. Right? Make it short. You know. It's just aggravating, right? So, and then over here, rather than that, make it a 16-bit integer, right? And now we've got 10 plus 55 equals 65. Okay. Yeah. Frustration. So, what does that have to do with what you're asking about? Like, how do you add to a letter? Well, check this out. To a type purist, this probably should not compile, right? Because I'm not making a character. Like, a character should hold characters, right? This is an unsigned 8-bit integer. But I can set Sydney equal to A. And you're like, but it's a character. No, it's not. It's an integer. Anytime you see single quote anything, it is doing an ASCII table lookup, and it will put the ASCII value here. This is exactly the same thing as if I had said the number 65. Okay? So if I save this and compile it, you will see that it is now 10 plus 65 equals 75. Okay? That makes sense? It shouldn't make sense, but it does, maybe in some weird, twisted way. So if we, you know, were to actually just output Sydney without converting it to an int, you will see it turn into the letter A, even though it is an 8-bit integer and probably shouldn't be. Okay? 10 plus A is 75, right? And so if we add 10 plus A, and actually let's turn this into a char, like that. Now 10 plus A is K, right? A, C, D, E, F, G, H, I, J, K. Yeah. 10 letters later is K. All right? Okay? You guys understand? So what I did in my code, up here is I took letter 65, letter A, number 65. It's just numbers. Remember, a single quote is literally just a number under the hood. There's no separate type for characters. Okay? And integers. They're literally the same. To C++'s detriment. And I mean that in all seriousness. This is a constant aggravation for me. Like when I'm working with image data, which I do a lot, image data is 8-bit unsigned chars, right? So every time I try printing out the RGB value, if I try printing out 65, 65, 65, which is a medium gray, it prints AAA to the screen. And I'm like, and then I have to cast it to an integer or a short or whatever. And it's just like, all the time. Just all the time. It's just annoying because there's no separation between numbers and letters. But in this case, we're putting it to use. So what's happening here is we're taking the number 65 and we're adding 0 to it. So 65 plus 0 is 65. What ASCII code is that for? A. And so for the first child, as we recurse down to the first child, which is the A child, we're taking whatever string we have, like for hello or whatever, and this is the string append operator. So strings can have two things appended to them. They can have other strings appended to them, and they can have characters appended to them. So you can append one character at a time to a string. And so we are appending 65 to it. Okay? And so it is of type char. C++ has a plus operator overloaded for strings that takes a char. So it takes ASCII code 65 and attaches that to the end of the string. Okay? Next time through the loop, I is 1. A plus 1 is B. Next time through the loop, I is 2. A plus 2 is C. And so for each of the children, it will get the letter that corresponds to their direction added to the string. Does the trie have the whole dictionary? No. The trie only has the words that have been entered by the user. The dictionary down here is only used to right here. It's only used to filter words that go into the trie. So the trie only gets valid English words because Aaron wanted spell checking. So I'm like, all right, yeah, we can do that in like 4 lines, you know. So here we go. We open up the dictionary. If it failed, we die. We make a hash table of all the words. All possible words are either in the English language or not. And we just say, while there's words left in the dictionary, insert it into the English language, English set, uppercasing it. So we have the uppercase version of every word. So we don't have to worry about case sensitivity and stuff like that. So we read one string at a time from the file, uppercase it, put it into the hash table, and then later on we just say, hey, if the hash table contains that word, we allow it. If it doesn't, we throw a America error. All right? Easy spell check. All right? So, makes C++ sense. Yeah, that's funny. All 8-bit integers are cursed. Yeah, they really are. And it's frustrating because I do a lot of math because I do a lot of image processing stuff, you know? And the C++ just always insists that my image data are letters, you know? And it's just like, okay, they're not. They're really not. They're numbers. And you can't really represent it. So, I mean, it's not the end of the world, you know, to do that. But it's just like, again, yeah, okay, fine. Putting all the English words in are surprisingly fast. Yeah, and that's in part because I'm using readlib. Readlib is nice. And so I say read one string at a time from the file, and then the results of that get passed to uppercaseify, and the results of that get passed to insert. And so this would be more lines of code if you had to do it with double right arrows and stuff like that. Because IO in C++ is not... It probably should be a function, let's put it that way. And on the output side, there's something called format, FMT, which is a way of printing things more succinctly and compactly than like that, with all the chevrons and stuff like that. But on the read side of things, it just sucks to be you. You know, like, there's a really good reason to do input as a function, because you can do things like this. You can chain together your input with a function and then have that go into a data structure, and all that chains together. You can't do that with chevrons, with the double right arrow. You can't embed a double right arrow that easily into things. Like people will put it into like a while loop to see if an error occurred, but you can't do this because it's a call by reference kind of thing instead of a functional thing. Okay, you can't get your head around what worked. This thing here. So we got a file, ends. Readlib is templated, so you tell it what kind of thing you want to read from the thing. Do you want to read an integer? Do you want to read a string? If you're setting it into a variable, it can actually deduce its type from the left-hand side, but in this case, there's no variable, so you have to templatize it. So we're going to read one string from the file. The results of that get passed to uppercaseify. Uppercaseify just does that. It just uppercases the string and returns it. And then the results of that uppercased string gets stuffed into the hash table using insert. So, and then once the thing hits the end of the file, then it quits. And there is a bug in here, which is that the last file will get read twice. The last word will get read twice. And the reason why it gets read twice is because when you hit end of file, it throws an error. And so the string will typically contain the last string that was in there. And so it'll insert the last word twice, but it's a set. Who cares? It discards the duplicate anyway. So it all works out nicely. Can you visualize the recursive call step by step? Sure. Let's trace this execution. All right. All right. Recursive print. All right. Okay. So here's our trie. Our trie is already built. Okay. I should have needed that. So we start off with temp. Temp is going to point to root. And we have s is equal to null string. That's how we begin our function call. If you come down here and see where it goes, we pass in root and we pass in an empty string. Okay. There we go. So is the root null? No. All right. We got a thing. It's not null. So we continue on our merry way. Is root a leaf? It's not. So we don't print anything. Cool. Now we're going to look at all 26 of root's children. A, B, C, D, E, F, G, right? For our previous example, I think they all started with H, something like that. So we'll say this is the H direction here. And direction's maybe not the best word, but you know, whatever. Erase my trie and just draw it. So let's say we've got the words hi, hello, and hell, and howdy, and ha. Okay. So all the other pointers are null, and so when we're in root, root is going to only recursively print down in the H direction. Okay. Help. Yeah, that's good. Very suitable for CSI41. Okay. So we've got all of our kids here, and we're not a leaf, so we don't print anything. And then it's going to recur. It's going to loop through all the kids. Is there an A? No. Is there B? No. Oh, actually, there is an A. Sorry, I misspoke. So we have that. Now, when it recurses down in the A direction, it's going to call the function on the pointer in the A direction, and it's going to take our current string, which is H, right? And it's going to append A to it because this is the first kid. So the A kid is going to take H and have A appended to it. So it's going to pass to the function here. Ha. This is actually a string, not a character. So it's going to pass ha to it. Now this bad Oscar here is marked as a leaf, so it will print ha to the screen. So our cout is going to have a ha in it. And then it's going to call all 26 of the kids here. It's going to call the null, 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 and then it returns. Then it comes back up here. And then we're back in H again. So we check C. Do we have the B pointer? No. Okay. Actually, it calls it, then it returns. C, no. E, no. Oh, F, E, E, yes. So we recurse down into the E node. And so the string passed to it is HE, like that. And then before we continue on with the other letters, it's going to then call HEA, HEB, HEC, HED, so on and so forth, until we get to HEL. All of these are just going to return because they're all null. But HEL is going to go through, and then it's going to recursively call each of that guy's kids, HELA, Hela. Right? For those of you that are fans of Norse mythology, Hela is, of course, the goddess of the underworld. Thor's sister in Ragnarok, which doesn't exactly follow the Norse mythology very well. She's actually Loki's daughter, and she's half alive and half dead. Quite different in the Marvel universe. Okay, Hela. Anyhow, so HELA, HELB, we're going to get down to HELL, HELL, and that's marked as a leaf, so that gets printed. And then we recurse down into help and hello, and it's going to just traverse the whole tree. Anything that's marked as a leaf is going to get printed, and then it returns back up. Then it's going to go to I, null, J, null, K, null, and then it finishes it out. Okay. That makes sense? There will be 26 to the nth power calls, where n is the number of letters in the string. If you have that many things, right? So like it doesn't recurse down into like Z, like it goes into Z and then it immediately returns. So no, it's proportional to the number of nodes in the tree. So that it's order n basically. This is an order n print where n is the number of nodes in the tree. And it's actually going to be faster than this, right? Because if you were going to print all of the letters in the English dictionary, there's a lot of overlap, right? And so it's actually, well, I mean, you still have to print the string, so it doesn't really save you that much. But in terms of like storage, at least in the dictionary, there's a huge amount of redundant, wasted space, right? Because all these things have substrings that are the same. HEL, HELL, HEL, H, same for all of them. And so the trie uses less space, arguably, even though probably the pointer array is going to be way bigger than any savings. You don't actually have nodes proportional to the English, language if you fed the dictionary in, but substantially less. Okay. Is children an array of zeros? Children is an array of pointers. So children is all of the pointers to our kids. So, like I said, these are shared pointers. They probably should be unique pointers from a philosophical perspective. But like I said, there's no way in the standard library to traverse a tree of unique pointers without using raw pointers. And you can. I actually wrote this the first time using a raw pointer. But I just don't like the type. Yeah. Okay, so yeah, it's an array of pointers, and they all get initialized to null. They're all null initialized. So if you wanted to, you could you make this code arguably probably a little bit faster by saying if temp points to children I, then recursive print. So don't bother printing the kid if it's null. So that'll save you the function call in and the immediate return back out. So you can do this. It'll probably run a little faster. It's the same because we're checking for a null pointer here. So. All right. So let's talk about your homework. So we're doing so that's tries. That finishes off tries. What we're going to do for the homework assignment is we're going to combine a priority queue, which you built in histogram, with a trie. Okay. And I'll copy this code up here, copy main.cc into /public trie.cc so you have a copy of it. And let's talk Huffman coding. So the way Huffman coding works is you build a min tree. Okay. Your histogram, I think, uses a max heap or equivalent thing. Let me just show you my histogram. Histogram.cc. So my the way I sorted the characters, first up top I printed it in ASCII order. Now I'm going to print it in count order, right? And so basically, for each of the buckets, I add it to the priority queue, and then I pop everything out of the priority queue. So this is heap sort. Heap sort is push everything into a heap and then pop everything off the heap, and they come out sorted. It's heap sort. It's very easy. It's like a couple lines of code to sort something. So I'm pushing all of my nodes, I think I call them, and a node is just the ASCII, like the letter S, and S appeared 7 times, whatever. And that gets me to the top of the heap. That deletes the top of the heap. I personally think that the priority queue should, when you call pop, should return the top anyway. I think there's, I remember reading a reason why they don't do that, but whatever. I guess so you can get the, I don't know. To me, pop should return the node, but whatever. So this gives you the top of the priority queue. That is the, for Huffman coding, it's going to be the lowest count character. And then I'm just printing it to the screen. So this isn't Huffman coding, this is histogram, but this is basically what your code's going to look like for Huffman coding. You're going to histogram everything. You're going to put them all into a priority queue and sort them by count, least to greatest. It's the opposite of your homework assignment, which is sorted greatest to least. And then here's the algorithm. Okay, so the algorithm. Let's draw it. I got slides too. I can show you the slides. I'll play a video for you too, so you can see what it looks like. But this is what it looks like for Huffman coding. Step 1, pop the top 2 nodes off the heap, the priority queue. Make a new node. Whose count is the sum, and link it up. I'll show you what that means in a second. And 3, push new node back onto the heap. Okay, that's it. You do this in a loop until the heap has exactly 1 element left in it, and that is going to be the root of the trie. So this is constructing a trie. And why 2? Because the first is null. It's going to look. Let me show you what it's going to look like. So let's say you've got a that's got 10 letter A's. There's like 12 E's. There's like 1 J. There's 2 Q's. There's, I don't know, 5 U's, and I don't know, S's. There's like, I don't know, 7 S's or something. I don't know. So the priority queue is going to sort all of these smallest to greatest. So this is the first one. This is the second one on the heap. Those are the smallest 2. Okay, so these 2 guys are going to get popped off the heap, and you're going to get a node made for both of those. And you make a new node that points at both of these. So J with a count of 1, Q with a count of 2, and then the new node doesn't really have a name, it just needs a count, and 3. And then this goes back into the priority queue. So we'll just call this one JQ, the count of 3. Doesn't really have a name, but just to keep track of it. So there you go. And now the priority queue does its magic. And what are the 2 smallest nodes now? What are the 2 smallest nodes in our priority queue here? Yep, the new guy, JQ, and U. So both of these are going to get popped off the priority queue. And U, count of 5. And we make a new intermediate node, and that has a count of 8. And the left pointer is here, the right pointer is here. It doesn't matter which one's left, which one's right. And we'll call this one JQU, just keep it straight, and it has a count of 8. Who are the 2 smallest ones now? Clean up a little bit. JQU and S, yes. So the new one we just added, you don't always pop off the one you just added. It just kind of worked out this way. Just has to do with the numbers. So we got JQU, which is this one, and S. So S has a count of 7. And we make a new intermediate node that has a count of 15. 8 plus 7 is 15. And we push that one back onto the stack, or onto the heap, sorry. So these 2 guys are gone. Running low JQUS with a count of 15. Who are the two small ones now? E and A. Yeah. So this is not part of the current tree. We actually will start a new tree. One with A, one side with A, one side with E, and an intermediate node with a count of 22. And so you actually grow a forest of trees. Now at the end, they're all going to be merged together into one tree, but that's quite common. And you don't have to worry about any of this stuff because these things are all going to be in the priority queue, and they'll have pointers to the permanently allocated memory for these things. And then, yeah, so that intermediate node there gets pushed onto the stack, and that one we'll call AE with a count of 22. And now we pop the last two people off the stack, and when we push the intermediate node on, we're going to have one person left, so we're done. After we do this step, and let's get my face out of the way. No, whatever. All right. We're going to go sideways here. So here's the root. There. And there. And its value is going to be 37. Okay. So there are 37 total characters in our document, and we now have a trie. Okay. And you might be like, all right, what do we do with this trie? Well, Huffman coding is used for text compression, right? So you're like, all right, how the hell does this compress a text file, right? We just built a trie. What the hell? Well, watch this. Let's say that, you know how before we had 26 kids? Here we only have 2 kids. This is a binary trie, okay? And going left, let's say, represents binary 0, and going right represents binary 1. Then each one of these letters is going to have a binary string associated with it, just like what we did there, that you build up by going left and going right, appending either a 0 or a 1 to each one. And if you wanted to print out the dictionary, J would correspond to 0, 0, 0, 0. Q don't write J twice. Q would correspond to 0, 0, 0, 1. U would correspond to 0, 0, 1. S would correspond to 0, 1. A is 1, 0. And E is equal to 1, 1. Now, what do you notice about this? Which one of the letters had less common count? Which one of them had the lowest count in the histogram? And which ones had the highest count in the histogram? What do you notice about this? What do you notice about the length of the strings? Notice anything interesting? What can you tell me about the letters that occurred more often in our histogram? Yeah, the ones that happen more often, letters like A and E and S, they only have 2 bits associated with them. Whereas J and Q, which occur less frequently, have more bits associated with them. And so if we were to try to, like normally when you encode something in ASCII, you're using 1 character per letter, right? ASCII is a 7-bit system, but we usually output 8 bits just to make everything line up nicely, right? So normally, if you were to output A, you'd be outputting 0, 1, 0, 0, 0, 0, 0, 1. It's gonna make, yeah, 65. Okay, so that's 65. Under Huffman coding, that was not the eraser. Ah, you're doing the thing again. No. Switch tabs. No. Doing the thing where you can't click on the thing. Okay, whatever. So here we have 8 bits. Here it's only 2 bits. So if we were to encode the string like this, this would have been 8 bits times 5 letters. This would be 40 bits normally. But if we did Huffman coding, this would be 1010101010, which is 10 bits. Cool. That's a 4-to-1 compression. Check it out. Kind of neat, huh? Kind of neat. Windows Update, I don't know. This This bug has been going on in OneNote for years. And the only sometimes you like switch tabs and switch back, it starts working again. A lot of the times you just close out of OneNote and then come back in, and then all of a sudden, it'll start working again. I don't know. You'd think that Microsoft would be able to hire computer science people worth a damn, but it's Microsoft. So. We just have people like Muya. Oh, he's not here right now. one of my former embedded tutors is now working at Microsoft. So, all right. You guys see that? You guys see how that worked? Looks like magic, right? We just we had a histogram and we built a trie using the histogram. Pop 2, push 1, pop 2, push 1, pop 2, push 1, until the thing goes down to one node left. That node is the root. And then just the position in the tree is the bit pattern that corresponds to that letter when you output it. So if you were to output JQ, it would be 1, 2, 3, 4, 1, 2, 3, 1. It would be 8 bits. So that would be a 2-to-1 compression ratio. Okay. You guys see that? Kind of cool, right? What do you guys think? So the whole point of Huffman coding is that you get a Hamlet or something like that, right? You get a big body of text, and you do a frequency analysis. That's a histogram. That was part 1. That's what you guys did do today. And then you output the dictionary. So there's an overhead to this. There's an overhead to the dictionary being output. So you don't use it for like a paragraph, because the dictionary is going to be as big as the paragraph, right? But for like Hamlet or the complete works of Shakespeare or something like that, you do a pretty comprehensive analysis. You build a trie using it like this, and then the bits that you actually output, the more common the letters are, the less bits they use, and the less common, the more bits they use. And some of them that are very rare might be 13 or 14 bits. It might actually be more than the 8 that you normally use, but it still saves space because they don't come up that often. The ones that come up all the time, A, E, S, T, that kind of stuff, the letters that you see all the time in the English language will have very few bits associated with them. And so it's a net gain. And you usually get compression ratios of 1.3 to 1, 1.5 to 1 for common, things. Okay. You want to go back to 40? You can never go home. Retrogressive. Okay, but the good news is, if you don't want to do Huffman coding, and it's really like, I can show you what the code looks like. It's it basically, this is at the bottom of my histogram, right? I basically, you just pop off 2 nodes, make a new node where the count is the sum of, this looks garbage, but it's basically summing up the count of the 2 people that just got popped off. I popped them off and stuffed them into a vector to hang on to it. So I add up the sum of the counts, and that's the new guy's count. And then I make a pointer to the first guy I popped off, a pointer to the second guy I popped off, and then I push that guy back onto the prior DQ. And at the end of all this, root is now pointing at the top of the trie. And then you would use the code we wrote earlier in the class to go through the trie. Every time you go left, you append a 0 to the string. Every time you go right, you append a 1 to the string. And then you have your dictionary. The letter J corresponds to 0010. Letter Q corresponds to 1100. And that's it. That's Huffman coding. It's a partnered assignment. You can work with a partner. Do next Friday. If you don't want to do that, we can talk about that. So there's an obvious question here, though, right? Which is like, if somebody writes like, if you're decoding and you get like 101, right? How does that decode? Is that going to be like the letter S here, or is it going to be the letter A? Like, how do you parse that? And the answer is, to decode it, what you do is you read 1 bit at a time, and all these things are going to be stored into a hash map. This is the key, and this is the value for deciphering. It's kind of the other way around for encoding. For decoding, which is extra credit, basically you read a bit at a time, and if they type in 1, let's say they 110010, I'm just making up bits here. when you decode this, you grab the first bit, 1, and you see if that's in the hash map anywhere. Is it? Nope. Okay, grab the second bit and append it to the first. So now we have 1, 1. Is 1, 1 in the hash map anywhere? Can anyone tell me? Yes or no? Do we have an exact match for 1, 1 in there? And one of the beauties of doing a try like this is that it will never be ambiguous, because none of the leaves have anybody below them. Therefore, it will never be ambiguous what the parsing of it is. You start left to right, and you will always get the correct answer unambiguously every time. So yeah, this is the letter E. So this is going to output the letter E, and then we kind of clear those bits out, start over, read the letter O. Does O appear anywhere in here? Nope. All right, move on. Append that, O. Is that in here? Nope. Okay, read the letter 1. Is that in here? Yes, it is. That's U. Okay, so it's going to print out EU, Europa Universalis. Okay, start over. 0, S. Not yet. 0, 1, S. Okay, U's going to pay for this. Yeah. And it's doing the bug again. Yay, good job, Microsoft. Such a quality company. Just scratching all off like that. Okay, do you see that? So you just basically append and append and append. And once you get a hash map match, you echo the character to the screen and start over. Just keep pulling bits. You know, it's actually not hard to write. So this is traditionally a junior level programming assignment. I like to give it to my college freshmen so that I have bragging rights with my former professor, who doesn't articulate this class because he doesn't trust that community college students have any quality, so he makes them take it anyway. And I'm like, bro, we cover more than you. This is a junior level assignment at UCSD. So. You're pinning all to a string, or is this all binary math? This is not binary math. It's actually a string. Well, kind of. There is binary bit field stuff that's taking place, but I've done that for you. So it will just return true or false every time you read a bit, and then you just do the matching on it. For decoding, you don't have to do decoding by default. So that's basically Huffman coding. You pop 2 and push 1, pop 2, push 1. Keep doing that till you get a root, and then you just traverse the tree like we did earlier to come up with the dictionary, and you're basically done. That'll be due next Friday. Another option for being due next Friday is a bit field assignment, because we did not do anything with bit fields as far as homework goes. So this is actual code taken from Quake, and it's very similar to kind of code that I've written many times in my life and I'm very familiar with. So let's say that you're making a video game and you want to have an inventory system, and you don't want to have, you know, a bunch of different variables for true or false. Do I have the red key? Do I have the blue key? Do I have the yellow key? Et cetera, et cetera. So what you do is you make one int that holds all the possible values for a key. In this case, 1, 2, 3, 4, 5, 6, 7, 8. So technically you could hold it using an unsigned 8-bit integer if you want. I think for this assignment we use 64 bits for all the bit fields, but it doesn't really matter. Yeah. So, I mean, it does matter, but like not for this assignment. So, what's nice about this is that you have only a single variable that contains all of the keys that you have, true or false. And normally, if you had these in like 8 different variables or in a vector or something like that, then every time you did a load, it has to hit RAM, right? And hitting RAM is slow. And if it's on cache, it's actually very slow. And then you're like, do I have the red key, true or false? And it has to load from RAM. And you could do like maybe 100 additions in the amount of time it takes for RAM to return, no, you don't have the red key, right? And then you're just like, oh, well, do I have the yellow key? Hit RAM. No. What about the green key? 100 cycles later. No. If all of these are held in a single 32-bit integer, let's say, one load gives you the answer to all of your keys, right? It's actually much faster. And so this is one way of doing constants in C++ using enums. It's essentially the same thing as writing constant key equals 1. There's also something called enum classes, which are a little bit stricter than regular enums, but we're not covering that in this assignment. Another way you can do it is just to make a bunch of constants like that, and that's fairly common in industry. Just people just make a bajillion globals that have powers of 2. Like, all those are powers of 2, and this is how you do it in C. So you'll see this all over the place in industry. Hashtag defined weapon hook. Hashtag defined weapon axe. All powers of 2. And this is not in the actual Quake. It's named after David Navarro, the counselor on campus. No, actually, his son, Josh Navarro, who was one of my students a while back. Okay, so this is we do a type def here, which is essentially the same thing as using uint 64 equals uint 64t. This is the C++ way of doing a type alias. So these are used in C world all the time, type defs. The C++ syntax is more, it goes the right way because everyone gets the type defs backwards. It actually kind of makes more sense to use it the using way. It can also do more things, like you've seen using namespace standard and stuff like that. So using is a little bit more powerful than type def, but these two lines are essentially the same thing, which creates a new variable type that's an alias for another variable type. So this is a unsigned 64-bit number, which we could call a uint64 also if you wanted to, which I kind of like better than int64 because int64 seems like it should be signed, I think, right? And this, we should probably emphasize it's an unsigned. All right, watch this. Next. Oh, is that it? I guess that was all the uses of it. All right. And so what you're going to do is you're going to make a couple classes using inheritance that work like bit fields. And so basically, it's going to be kind of a C++ version of int, right? You know how I said int was a data structure? You're making a C++ version of int, right? In this case, a 64-bit int. And so you're going to have a constructor that initializes it. You have a print function or whatever. But basically, you're going to overload 3 operators. So plus equals will set a flag, minus equals clears a flag, and double equals tests to see, searches to see if that flag is set. And so these are going to be just one lines each. If you go back to our lecture a couple times ago on bitwise operations, there's a PowerPoint presentation if you want to look at the code. It's pretty simple. They're going to pass in like weapon axe, and then you return, you return true if weapon axe is in the bit field, and you do so with the ampersand operator. Plus equals will use the bitwise or operator to set it, and minus equals uses and with the bitwise not of the flag to clear it. One line of code each. Okay. What is a flag? A flag is one of these things. So for example, job thief is a flag. It's a Boolean value that is either true, raised flag, or false, lowered flag. And we thank you for asking that question, because I do use jargon. Even though I try not to. I try to use plain English as much as possible. It's kind of a thing for me. But each of these are flags. Weapon hook is a flag. Weapon medikit is a flag. So you pass in a flag saying, pick up the medikit. And so it'll look like this. Like that. So plus equals the axe. And so that means pick up the axe. So you have a weapons bit field that holds all the weapons you have, and if you plus equals the axe, then the person now has the axe. It tracks inventory. If you want to drop something, you use minus equals. So this here is going to set the flags for red, green, and blue. So you have 3 keys in one operation. That's another really nice benefit of bitwise operations, is that rather than taking 3 separate, pick up function calls or whatever you want to call it, you can actually set and pick up all 3 at the same time. And here we are dropping 2 keys at the same time using bitwise OR. You can drop both the green and the blue key at the same time. And then double equals tells you if that flag is set, if that particular bit within the bit field is set. So if the keys bit field has the red key, then we'll print out has red, and that adds the axe, and yeah, so. And the word flag is used all the time, and open, right? So if you want to open a file, you pass in this is a string, right? This is a cworld string. You pass in the string containing the path of the file you want to open. Then you pass in flags. And so flags is an int. It's a data structure. It's an int. It has 32 different possible booleans that are set or not set. And so flags refer to individual bits within a bit field usually. So you pass in a set of options to the function call. And if they're true, they're set. If they're false, they're not set. Okay. And so it'll have a list of all the different flags. Here you go. Full list of the file creation flags and file status flags as follows. And these are all powers of 2. What power of 2 is it? Who cares? It's a power of 2. So that means none of them conflict with any of the other ones. Each one of these flags corresponds to a single bit within that flags field. So I don't actually know, I don't care if append is 8 or 2 or 16 or 32. All I know is that because they're called flags, each one of these values is a power of 2, and they're all different. All right, so yeah. And the lingo. Okay. So you have to make 3 different bit fields though. The basic one is pretty easy. Each one of these is 1 line of code, and you can just copy and paste that out of the PowerPoints. Okay. Yeah, and then you can pick up a flag, drop a flag, test to see if you have a flag, and that's it. These things aren't marked virtual, by the way. Right. So yeah, it's not. Yeah, you might want to. I don't know. I don't think we're actually using any sort of dynamic runtime polymorphism. So I think you actually don't need to, but you might want to mark it as virtual. Okay, so there's the bit field class, which is your basic. You can set a bit, clear a bit, test a bit. That's it. Then there's 2 specialized ones, and this is kind of a thing in C++, right? Where like, let's say that you want to have a flag that is mutually exclusive with another flag. And so maybe out of the 32 bits possible, 10 of them are mutually exclusive. If you have it set for to delete the file when you make it, that might be mutually exclusive with preserving the file or appending to the file or something, right? And so you can enforce the fact that both of those can't be set at the same time by wrapping the bit field in a class. And so in this case, for the jobs bit field, there are going to be, you're going to overload the plus equals operator. The other 2 operators you're going to leave the same, actually. And that's one of the nice things about inheritance. It just copies and pastes all the code over, and you don't have to change most of it. You just only have to change things different. And so you're going to overload the plus equals operator and say, if this thing is set, then you have to clear these other 9 bits or whatever, right? And if you set this bit, then this one gets cleared. And if this one gets set, this. And so of these 10 bits, they're all mutually exclusive. If you set any of them, all the other ones get set to 0, leaving the rest of the bits alone. And so no more than 1 could be set at a time. None could be set, but if you have 1, it clears all the other ones in that region of the 32 bits. So that's the jobs bit field. They're mutually exclusive jobs. Basically, in the video game that I wrote, if you have a job, you can't have another job. It's not like real life where you have 4 jobs or whatever in real life, which I think I had right at the start of the pandemic. I think I was technically employed in 4 different places at the same time, which sounds pretty impressive until you look at the the number of hours I spent. I was teaching 1 Taekwondo class a week and getting paid, I don't know, it's like minimum wage, I think. I was paying my babysitter, I think, twice what I was making teaching Taekwondo. Because I wanted to do it for free, but they're like, no, we have to make you an employee, and America's stupid when it comes to labor laws and stuff like that, so they were paying me less money than I was paying my babysitter to cover for me when I was teaching Taekwondo. So I was doing that. I was teaching at Fresno State, teaching at Columbus Community College, and then I have, of course, my own businesses. So sounds a lot more impressive, just put it that way. In real life, you can have multiple jobs. In the video game, you can have 1 job. Okay? So when you set a bit, then you clear all the other bits for the jobs and then set it. And then the other ones are left the same. And then the weapon bit field doesn't change any of the plus equals, minus equals, equals operators. Instead, it adds a new function called select best weapon. And if you remember a couple lectures ago, I showed you how to use bit shift. And so for select best weapon, what it's going to do is return the flag, the bit corresponding to your best weapon. And that's based on a numerical comparison here. So the super nail gun is somehow better than the laser cannon. Doesn't make sense to me. The railgun's better than the tranquilizer. The dataless is better than the lightning gun, and so on and so forth. So basically, you start a bit up at high, and you sweep it down. First time you find a bit that's set, then you return that value. That's it. All right, see you over. This assignment should be doable for all of you. You've done inheritance twice now. I showed you macroing last time because you're going to have all this stuff, and you're going to have to use macros to have an if statement, like if the user types in weapon incendiary, return weapon incendiary. So hopefully you're paying attention when I was going over Vim macros. If not, there is a file in here called macron.txt. No, that's the president of France. Macro.txt, and so it has all the instructions on how to do macroing, or at least the commands needed. You can look at the lecture online to see how to do it. So you'll probably need to use your macroing skills to convert text into text. Yep. So probably, I'd say 7, 5, 3 hours of work. I don't know, something like that. Not too bad. Huffman Coding's actually not that bad either, except it melts your brain, right? Huffman Coding absolutely melts your brain, and that's part of the beauty of computer science is you keep getting your brain stretched, and as your brain stretches, it grows, and you become better and more competent, and things like that. So I will allow you to choose which one of these 2 assignments you're going to do. This is individual. Huffman Coding is partnered. Okay? Turn in either of them by next Friday. If you want extra credit, you can turn in the other one by the last day of school. Okay? And so May 20th, where we're having our potluck and get together and party and stuff like that, May 20th is the deadline. And don't do it at midnight. Do it at noon on Friday. Okay? And then you can get the other one done. And if you want extra credit, on top of the extra credit, the Huffman Coding has a optional thing to decode it, which I already went over. It's just having a hash map. It's not actually that bad. And that's an extra letter grade on top of everything else. Okay. Either one. Yeah, you can do either one, and then if you do one, then you can do the other one till the end of the semester. So, and that'll make up points for any assignment you missed or barfed on or whatever. I've gotten all of your RPGs graded. A few people forgot to put in the bullet points. They did, and I didn't really feel like going through their code looking for things, because I use your bullet points, the self-report, as my guide to your code. And so I just gave people whatever they put down. If they put down 0, I give them 0. And so if that happened to you, message me, and I'll and then tell me which bullet points you did. Then I'll look at your code. So all the RPGs have been graded, and I've gone through all the Spring Break, BST, Bonanza things, except for the ones where they added the extra credit to the RPG assignment, because I just graded the RPG assignment, and that needed to be done before the extra credit could be awarded to it. So that should be coming online, I don't know, in an hour or so, once I log off from here. Okay, I'm not going to give you an F. It's just, like whenever I have a requirement like, hey, report these things to me, and you don't do it, it's like, all right, you get a 0. And then that usually wakes the student up, and then they're like, wait, why did I get a 0? Well, you didn't tell me. Oh, here's what I did. Okay, thank you. I don't have to sit there and dig around. Is there a map somewhere within here? I don't know. So, I can't find it, but, it's a lot easier if the student just says, I didn't do the map. Thank you. Now I don't have to look for it. Okay. That's basically class today. I'll play... Screenshot. Yeah, the screenshot's good enough. I'm going to play a video on Huffman Coding so that maybe you guys can understand it a little better. I kind of went at it the back way. Like, what the heck is that? Jordan Peterson, round. This is such a weird thing that they're... Yeah, interesting. More best ever food. Why? So weird. Okay. Yeah, so I'll pull up a video on Huffman Coding, and yeah, this one's pretty good. I played this in the previous class. I'm not going to play it on the recording because I don't want to get a copyright strike, but yeah, no, I mean some of it's accurate. Like like you saw, I was just watching a Jordan Peterson video on academia actually, and stuff. It's interesting to me. But we got Japanese Inca. I got Trapinch and Shuckle. I literally don't know why. Julia Child on McDonald's. Why? Like, I don't... It's so... Yeah. It's such a random grab bag of things. Okay, so... Huffman Coding... And I'll play this, but that's basically our class. Both of the assignments have been pushed out to you. You have till next Friday to do one of them, and then the end of the semester to do the others. Okay, so I'm going to play this. Don't log off. I'm just going to stop the stream, and then after the video finishes, then you're free to go.